Hello. I decided to upsolve problem C from Shanghai stage of second Universal Cup 23. It's called equal sums, and it has a deceptively easy statement. So we have several, namely two sequences xi and yi. And we need to, and for each of them, you are given a segment, such that x is between L and R, and y is between L and R. And you need to sum them up in such a way that sum of x's equals the sum of y's. Moreover, you should do it not only for all numbers, but even for prefix. So you take only first a numbers x and only first b numbers y, and you need to sum them up. You need to find the total number of ways for each a and b, each pair. So the output of this problem will be a matrix. So what happened to prevent me from solving this problem was that I'm quite bad at DP, and first of all, it's not obvious that this is a DP problem. But secondly, so these constraints, they don't tell you much. So sometimes when you look at the constraints, you understand, you have like basic feeling of how the solution will go. But in this particular case, this 500 number doesn't tell you much. So it might be a FFT or a lot of FFTs, or maybe some DP. And if even DP, it's not obvious if it should be cubic or quadratic, or maybe even quartic, with some optimizations. However, so I wasn't able to solve this problem. I looked into a tutorial, and actually it's just a simple DP problem. It featured one cool idea, which I kinda know, but it didn't occur to me that you can apply it. So basically, we have, it's sort of like knapsack. So we have two bins and we have several objects. So assume that you did it and you ended up getting all these objects stacked like this. So we got some A and B and they are equal. Yes. Let's try let's try and take all the objects. So what can we do? Let's take first of all this object. Let's take then this object. Let's take this object, this object, this object from the. Let's, for example, this is weights. So this is weights, and they tell the difference between these two bowls. After that, you remove all these elements. Now let's look at some interesting restriction. Let's say that if the difference is too big, then the weights break. Namely, for example, note that all elements are at most 500. So let's say that if the difference is greater than 500 by absolute value, then the weights break. Okay? So, okay, they break. This is sad. But can we remove all the elements from here and here without the weights breaking? Actually, we can. And there is some simple algorithm to do it. So let's just look at the difference. If the right side is at least left side, if left side is at least right side, then we can simply remove any element from the left side. And if right side is greater than the left side, then we can remove anything from the right side. And if we do it, then we remove all elements and we get a difference of 0. So we can get any state with difference at most 500 by simply removing the element from the bigger bowl. Moreover, actually this weight is unique in sort of... So if we make this restriction so that we can only remove uppermost element and only from the bigger bowl, or in case of equality from the left bowl. With this restriction, there is only one way to get any such position. Exactly one position. So if we're interested in the number of ways, we are likely to enjoy the ways in which the processes during which the number of ways is preserved. So if something can be done uniquely, then it's something that we should pay attention to. Okay, so actually, if you notice this idea, then this should be some sort of easy DP. So let's write this. DP I j, for example, difference is number of ways to put first I elements on the left, then, sorry, next j elements on the right side, such that the difference left minus right is d. Okay? So if we're interested in only in equal sides, yeah, so let's look at what this difference can be. Let's, instead of 500, we take constant c, so each element is at most c. So can the difference be minus c, for example? Yes, actually it can. If we have two equal piles and we remove the element from the left one, we can get L minus R equal to C. However, if we remove the element from the right pile, it can only happen if the right pile was at least one greater than the left one. So if we remove from the right pile, then difference will be at most C minus 1. So actually this thing is from minus C to C minus 1. And since C++ is not rich in data structures which allow negative indices, let's instead move to this space from 0 to 2C minus 1. And in the end, we will just subtract C. As for I and J, they are simply from 0 to n and from 0 to n. Now we only need the initial conditions, the way to extract the answer, and the transitions. So the initial condition is definitely dp 0, 0, c equals 1. So there is one way to not take anything and just get the difference of 1. Okay, what about a dp? What about the answer? So we just want to get the 0 difference. So again, this should be c, yeah, because we added c to all to the third dimension to get this segment. So the answer to the problem for a and b is dp a, b, c. So this is the answer. And finally, we need the transitions. So let's look at the state dp I, j, s. How did you manage to get it? How did you manage to get it? So to get it, you need it to somehow come here from some other state. Yes? Well, let's see. If S is at least C, then that means that we need it to come here from dp I minus 1, j, and something. Yeah? We somehow need to come from dp I minus 1, j something. Well, let's think. So we know that in order to do that, we needed to take element number xi minus 1. And we know that it is from li minus 1 to ri minus 1. And if we subtract it from s, then this number becomes from s minus ri minus 1 to s minus li minus 1. So this is the segment of possible values. So actually, this number is simply the sum of these, because the process that I mentioned before is one-to-one process. So you get this thing exactly once from each of these things and from choices of xi. This is one-to-one mapping. So you simply can say that this dp is sum of dp I minus 1 j s minus x I minus 1, where xi minus 1 is here. So we need to somehow calculate this sum, but it is easier. So let's calculate dq I j s equals sum from k equals 0 to s minus 1 of dp ijk. This can be done in linear time for each ij, so total cubic time. And after that, this thing is just dq of s minus li minus 1 plus 1 minus dq s minus ri minus 1 plus 1. So very easy. Okay, and the same thing if s is at most is less than c, because in this case we need to add y. So this dp I j let me think. dp I j s equals what? Equals sum of dp I j minus 1 and s minus y j minus 1 for y j minus 1 in lj minus 1 rj minus 1 y. And this is also, no, s plus yj, and this is simply dq ij minus 1 s plus yj s plus rj minus 1 plus 1 minus dq I j minus 1 s plus lj minus 1 plus 1. So shouldn't be hard. And this time, since dp was with indices from 0 to 2c minus 1, then this is from 0 to 2c. There are 124 megabytes, so maybe we can even store everything of it without any optimization. But since I don't like it, even if it is possible, we won't do it. Instead, we will apply one more optimization, which says that actually each time when we look at this dp, we only need dp ij minus 1 and dp I minus 1j. And this means that we can make a graduation by parameter of I plus j. So if we only look at elements with fixed I plus j, we are only interested in elements for which I plus j is exactly one less. So we're only interested in these elements. And because of that, we only need quadratic memory. Let's try and implement this. So we read, first of all, we read n and m. Oh, I mean, first of all, I need to read input. Ah, I see. Also, I will need modular operations. So I need this modulus. And I need c equals 500. Okay, let's make int sum. Actually, I think, oh, we need sum and difference. Int a, int b, return, if a plus equals b is at least m, a minus equals m, return a. The same for the difference. Okay, then we need PVI find ants. And for that, we would like to have using vi equals vector int and using vi equals vector vi. So we will find ants given just these vectors and these vectors. So we need a VPII. Nice. And void solve tests and bool solve test. So is it multitest? It is not, but we will still make it a multitest. Okay, so we need here to solve tests. Now let's read the input. We need n and m, and then we need VPII, x and y. VPI X and Y. Let's read them. I need define X first, define Y second. Okay. We need to read p.x and p.y, and then again for y. Then we need find dance for x and y. Actually, we just need to write the matrix. For in j equals 0, j less than m, rewrite ans I j, j equals m minus 1, and return true. So we need to only find the answer given these VPIIs. Let's try. So we will have ans of size n and m, which we will return in the end. Great. So let's say that we want to store dp. So at the end of our iteration, we want to store dp I. So we want to store dpi, then we will skip this dimension because it will be, let's call it, for example, d minus I. So d, I would like this to be d actually. So okay, let's call this cs. So sum of our first two dimensions is s. So we store dpi s minus I, and finally here we have difference plus c. Here we have. So this is what we store. This is how many ways to do something. So we have VBI dp of size n, vi of size 2 times c, for example, plus 1. Actually, let's make it plus 1. And the only thing which is non-zero now is we take no elements from x, we get the sum of 0, and we get 1. Now we need to go through sums from 0 to n plus n. Okay. So let's assume that this has already all answers in which the sum of first two dimensions is s. Then we need to construct the new array for which it will be y. Okay, let me think for a while. Okay. Okay, first things first, I want to make from this dp array a dq array. To do that, I will do it in place. Yeah, and I simply say that now dp I from dp equals 2 times c minus 1, d is at most z is at least 0 minus d. I say that dp I d plus 1 is dp I d. After that, I say that dp I 0 is 0. And then I go through all these, starting with, I think, 2. Where I'll say that dp I d plus is sum of dp I d and dp I d minus 1. Okay, so now I have the array dq. Now my new array will be dr, and actually let's put dr here. Yeah, it will. So we will do it to not make a lot of allocations of memory. So dr will be a temporary array. Dr will store the answer. Actually, I think let's just clean dr manually. Or let's assume that dr is already clean. So dr is array of zeros. What we will do in the end? In the end, we will say that dp.swap dr. So now dp again contains all correct numbers, and we need to clear dr. So to do that, for int I equals 0, I is less than n plus plus I. Oh, I also want to have n plus 1 here, just in case. And here we need at most n. And here I say that dr I needs to be filled with zeros. And that's not it. I also want to store answers. How do we do it? Let's go through all numbers. It should be at most 10. And actually I can do it in this very cycle. So let's calculate j equals equals sum plus 1 actually already minus I. And if I is at least 1 and j is at least 1, then we can store it in the answer. So ans I j. No, I think it should be at least 1, but at most n. So then ans I minus 1 j minus 1 is dp IC. This is excellent. Now the only thing left is to store all correct numbers in dr. And we can do it quite easily. We need to iterate over all numbers from 0 to n. We need to then iterate over all numbers from s equals 0. So we need to calculate all numbers from 0 to 2c minus 1. Actually not s, but d. It should be d. And here it should be d, yeah. Okay, let's... I mean... Okay, we have two cases. First of all, S is less than C, so less than C. Yeah, in this case, we will pass to J minus 1. So let's look at J equals, let me think. So if we, now S is not S, but S plus 1. So we need S plus 1 minus I. And we need J to be at least 1 because we want to subtract 1. But J should be at most M. And if it's true, then we go in this 4. But also if J is at least 0, and J is at most M, and I is at least 1, then we can also look at all these from C to 2C. So here we need to only look at this case. So dp dr actually id can be achieved as sum of dp I j minus 1 over a segment. So we need to take still dri, but to do it over a segment we need to make this subtraction, so we will calculate. Okay, it's d plus rj minus 1, yeah, which is achieved as y j minus 1 dot second and plus 1 minus the same with dot x. Excellent. Okay, almost the same here. Yeah, almost the same here. But this case. So actually here we need to subtract xj minus 1. Oh, here we need xj minus 1. I minus 1 actually. And here it should be I minus 1. And here it should be I minus 1. Dot x. It should be plus 1 here, but it should be minus. And here we should subtract minus, again x, again I minus 1. And here we need y. Good. But this is not good because we need to store it somewhere. So actually it is stored in dpid. So dpid is sum of dpid and difference of these two numbers. And here dpid is also sum of dpid and difference of these two numbers. So that's actually basically it. We only need it to like work and get accepted. Let's try. We need to read the sample, which is only 1, unfortunately. And it is full of zeros, unfortunately. Okay, let's look what happened. So dp is for some reason always zeros. Oh my god. Okay, maybe I need to look at DP. Okay, since here all numbers are small, yeah, all segments are at most 4, I think. So we can take c equals 4. But since we will easily forget about it, I suggest using ifdef. So ifdef, like on PC, constant c equals 4, else 500. Good. So it should be still all zeros. But now it's not all zeros. It's again all zeros. But now it will be easier to look at it. So let's look at DP. It's all zeros here. Yes, it's just all zeros. And DR? DR is not all zeros. Wait, what? I want to do it in the... Okay, I need to... So I want to store... Okay, I think we will do it like this. So we will swap in the end. That's what I think. Okay. Let's try again. Again, all zeros. Why? It's not nice to say the least. So let's look at DP. So what is N? N is 2. So we need to have 3 DPs. DP0, DP1, DP2. Correct? So we need to have DP0, DP1, and DP2. It's all zeros. Why? Why is it all zeros? I don't understand something. The R was zeros because... Okay, at this moment, the R is not zeros, but DP is zeros, so I understand it. What I don't understand is why this is still zeros. Okay, actually we needed to do it here. So first of all, we make DP, then we swap it with DR. So now DR is old values and DP is 0. Then we fill DP, and then we clear DR and put the answer from DP to the answer. And it's still zeros. I am starting to feel tired of that. Why is it all zeros? What's wrong with you? It is all zeros. It's just all zeros. Why? Okay, let's look at dr0 maybe. Maybe I don't understand something. It's all ones here. Ah, it should be dp0c is 1, I think. Yeah, it should be dp. Still the answer is not understandable, to be clear. To be honest with you, the answer feels strange. But let's see. Okay, now it says, for example, what is this strange answer? Ah, it says that if I want exactly one so c equals what? C equals 4, correct? Yeah, correct. So I can take... No, I don't understand it. 1, 2. 1, 2 means that the sum is from 1 to 2. Yeah? No, I don't understand why it is only 5, only 5 here. It should be 5 or 6, yeah? Because if I take left thing, let's jump here. I said jump here. Ah, okay. So I want to look at dp1. So in order to do that, I need to look at dr. Yes, this one. So I need... So I think for d equals 6, I want to get non-zero. Okay? What? No, what happened? What happened? No. No. So I want d to be 6. Okay, DP is 6 here. Yeah? DP is 6. And it is said that DP6 is difference of DR6 minus 6 minus 1 plus 1, so dr6 minus... I shouldn't take plus 1 here, I think. Yeah? Because we have a segment, not an half interval, semi-interval. Semi-segment. Okay. Is it now correct? Yes, it is. Now we can even not fix anything because we already have this if-def. We can simply submit. So it is problem C. Custom test. So first of all, we check that in the system, this thing doesn't fail. And it doesn't. So we can submit. Compiling. Judging test 3. Well, it is not bad. It is not bad. And it's accepted, and it only took 8 megabytes of memory instead of our 1024, which is nice.